Electric potential and electric potential energy, going to be the topic of this lesson in my new general physics playlist, which when complete will cover a full year of university algebra-based physics. Now this is the first lesson in a new chapter on electrical energy and capacitance. And in this lesson we're going to introduce the idea of electric potential, which is intimately related to electric potential energy and hence the name, but something you're probably a little more familiar when it's identified as voltage, although not technically proper. But we'll talk about the potential due to a point charge. We'll talk about it a little more broadly and relate it to electric potential energy, as well as the work done in an electric field. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. So let's start with an introduction to electric potential. We'll find out in a little bit that the electric potential energy is directly proportional to this electric potential, and hence the name. Now the SI unit is the volt, and as a result, it's commonly referred to as voltage in kind of the everyday vernacular. So if you say what's the voltage of a car battery? Well, 12 volts. Well, again, the proper term is electric potential. We really should say what is the electric potential of the car battery. But most people kind of use voltage interchangeably with that, even physics professors. But on occasion, you will come across a professor who's a stickler on you using the proper terms. And if that's the case, by all means, use the term electric potential, not voltage. And the idea is that, they might say, we don't call distance meterage, so don't call electric potential voltage. Not usually the case, but just in case you've got a stickler, it is their prerogative. Use the proper term in their presence. All right, so we'll start off with an introduction to a formula for the electric potential due to a point charge. And it's going to look a little bit similar to what we saw with the electric field due to a point charge. Now with the electric field, it was the Coulomb constant times Q over R squared. It was an inverse square law, where here it's just the Coulomb constant times Q just over R. It's not inversely proportional to R squared, just R, the distance from that point charge. And the really, really good news is that it turns out electric potential is a scalar, not a vector. With electric fields were vectors. We had to worry about both magnitude and direction. And when we added electric fields, we had to add them as vectors. That might involve breaking them into components and using the Pythagorean theorem and things of the sort. Well, with electric potential, you will never have to worry about that. It is such fantastic news. It is a scalar. It has magnitude, it has no direction, and you're just simply going to add up values. If you want to find the electric potential at a point in space, look at the different point charges you might have and just add up the components together. Now, even though it's not a vector, only a scalar, and only has magnitude, it can be positive or negative. If you have a positive charge, a positive value for Q, it will come out to give you a positive electric potential. If you have a negative value for Q, it will come out to yield a negative value for the electric potential, just by plugging in the positive or negatives. And we're ready for our first question. So the first question says, what is the potential at a point in space? 1.0 millimeters from a positive 1.0 nanocoulomb point charge. And the second one, just like it, we'll do them at the same time. What is the potential at a point in space? 1.0 millimeters from a negative 1.0 nanocoulomb point charge. All right, let's do some plugging and chugging here. So again, we've got the Coulomb constant, same constant we were introduced to in the last chapter, 8.99 times 10 to the ninth. And that had units of newtons meters squared per coulomb squared. And we'll multiply that by Q, which in this case was 1 nanocoulomb, and that could be positive 1.0 times 10 to the negative 9 coulombs, or negative for the second question. We'll just substitute it right in. And then all over R, in this case 1.0 millimeters is 1.0 times 10 to the negative 3 meters. And if you look at your units here for just a second, so one of the meters is going to cancel, one of the coulombs is going to cancel, and you're going to be left with newtons per coulomb times the meter. So one way to look at it. Another way to look at it is you could look at it as Newton meters, which is the same thing as a joule. Oh, so it's joules per coulomb, and that's what a volt is. It's a joule per coulomb. All right, so we can see the units work out here. Now we'll let our calculator do the heavy lifting for us. But we could probably do this in our head. We probably could do this in our head. 8.99 times 10 to the ninth times 1 times 10 to the minus 9 is just 8.99. And then dividing it by 1 times 10 to the negative 3 is the same thing as multiplying by 10 to the third. And so we're going to end up with 8.99 times 10 to the third, which will round up to 9.0 here. So 9.0 times 10 to the third. And again, that's either joules per coulomb or more properly volts. All right. And for the positive 1.0 nanocoulomb point charge, that's the value. For the negative, it simply would have just been negative 9.0 times 10 to the third volts, because we would have plugged in negative 1.0 times 10 to the minus 9. Only difference. So there's our answers for the first two questions. Let's make this just a little bit harder. So this next question should look a little familiar. So it's very similar to one we did in the last chapter. It involves the exact same diagram. And the question says, for the following arrangement of point charges, at what location or locations along the horizontal axis is the electric potential zero? Well, in the last chapter, we actually found where the electric field was zero. And we took advantage of the fact that we know that force equals charge times the magnitude of the electric field. And we said if we want a position where the electric field is zero, well, then the force would also be zero. And we kind of envisioned having a positive test charge and just figured out, is there some place either to the right of both charges, in the middle of both charges, or to the left of both charges, where that force could be zero? If so, then we can figure out a position in that area where the electric field could be zero. Well, that's not going to work here because force and electric potential are not proportional, and so it's not going to work in this case in the same fashion. So we can't just envision a place where the force on a positive test charge would be zero. Not going to work. What we can do, though, is kind of factor in both contributions. So we've got a negative charge here, so where we can calculate a potential kq over r. So, and then we've got a positive charge over here, where we can factor in its potential kq over r. And just figure out, is it possible for these two terms to add up to zero at a certain location in space? And the idea that this term is definitely going to be negative because q is negative, and this term is definitely going to be positive because q is positive. And as long as they have exactly the same magnitude, then they'll add up to zero. And so if we envision kind of maybe a point in space off to the right here on this horizontal axis, is it possible that these could have the same magnitude? Well, we can see that the Q here of 9.0 microcoulombs is 9 times larger in magnitude than the 1.0 microcoulombs here. And again, we're ignoring the sign, we're just worrying about magnitude. And if it's 9 times bigger, the only way we're going to get exactly the same magnitude is if it's 9 times further away. But over here, we're closer to that charge, not further away. So that's not going to work. There's no way we could end up 9 times further away. So, but that is possible in between the charges. Again, we want to be, since the charge over here is 9 times larger, we need to be 9 times further away. And so we definitely want to be over here somewhere closer to the negative 1 microcoulomb charge. And what we're going to do is we're going to find a couple distances. We'll just call this x, and then we'll call the rest of this 10 minus x, since they have to add up to that 10 millimeters. And so in this case, we're going to end up with the k, and our q again is that negative 1.0, and we'll do times 10 to the negative 6 coulombs all over x. So, and then we're going to add that to k times 9 times 10 to the negative 6 coulombs all over 10 minus x. So, and again, these have to add up to 0. Now, a couple different ways we can go about this, but one, you probably can see that the KE's are going to cancel. Even the 10 to the minus 6's can be divided out of the equation as well. We're really just left with negative 1 over x. So, and if we add that term to the other side, you'll end up with just positive 1 over x equal to 9 over 10 minus x. So, and we'll see that if we cross multiply that, we're going to get 9x equals 10 minus x. We'll add the x to the other side. We'll have 10x equals 10 and x equals 1. In this case, that's 1 millimeter. And then the 10 minus x would end up being 9 millimeters. And we can see that, yeah, we're 9 times further from the 9 times larger charge, which is why this works. So if you plug in the 1 millimeter here, and the 1 microcoulomb here, and then plug in the 9 millimeters here and the 9 microcoulombs here, you'll see that it works out to give you exactly the same magnitudes, 1 negative, 1 positive, and they will indeed add up to 0. Now notice the question did say location or locations, because it turns out it's also possible somewhere over here. And the key is, because that's a 9 times larger charge, is it possible we can pick a location over here that's 9 times further away from that 9 microcoulomb charge? And so in this case, we got to define some lengths again, and I'll leave this up top. So we call this, let's go a little higher. Let's call this distance x, and then we'll call the total distance to the 9 microcoulomb 10 plus x. And we do the same thing. Now you can kind of reason this out for just a second. So, because the key is that 10 plus x has got to be 9 times further away than x. And we could just write that, instead of presenting it in this form like we did by factoring the entire electric potentials, you can go straight for that distance, just do the relationship we just said, and say that 10 plus x has got to be equal to 9 times bigger than plain old x. And you can solve it that way as well. In fact, we could have done it for that one as well, FYI. We could have just simply said that x is going to be equal to, 10 minus x is going to equal 9 times x, which is ultimately where we led right there. All right, but same place here, we'll subtract x this time. And so we're going to end up with 10 equaling 8x, and solve for x. 10 over 8, same thing as 5 over 4, which equals 1.25. In this case, that's again in millimeters. And so in this case, at a point that's 1.25 millimeters to the left of the negative 1 microcoulomb charge, there's a place right there where the potential is once again also 0. And what you find out is that you're 1.25 meters left of the negative 1 microcoulomb charge. You're a total of 11 10 plus 1.25, so 11.25 millimeters away from the 9 microcoulomb charge. And 11.25 millimeters is indeed 9 times bigger than 1.25 millimeters, exactly as we need it to be. So in this case, 2 different locations where we can get the electric potential 0 on that horizontal axis. Either 1 millimeter to the right of the negative 1 microcoulomb charge, or 1.25 millimeters to the left of that negative 1 microcoulomb point charge. Now, when we introduced electric potential at the beginning of this lesson, we said that electric potential energy was directly proportional to electric potential, and hence the name. And I want to pick that discussion back up. It turns out that electric potential energy is equal to Q times the electric potential. Again, potential energy and electric potential directly proportional. So you simply got to multiply by the charge. And if you look at this a little bit different, if we solve for electric potential here, so it's equal to potential energy per unit charge. And that's a great way to think of what electric potential actually is. It's potential energy per unit charge. And how do you turn potential energy per unit charge into potential energy? You multiply it by the charge. And that's why charge times electric potential gets you potential energy kind of by definition here. We can also look at this in terms of change. And it turns out the change in potential energy is proportional to the change in the electric potential, the change in the voltage. And by the way, that change in electric potential is often referred to as the potential difference as well. You should recognize as such. So delta V, change in potential, i.e. potential difference, same thing. So I want to compare electric potential and electric potential energy to gravitational potential energy for just a second. If I let go of this marker, you all know what's going to happen. It's going to fall to the ground. And as it falls to the ground, it's going to lower its potential energy. So, and if you think about this, this is kind of the way it works in terms of potential energy when you're dealing with conservative forces. If something does something spontaneously with no outside work being done by any kind of outside force, so an object will always move in the direction to lower its potential energy. So, and again, from a gravitational sense, it lowers its potential energy by falling down. So keep that in mind for just a second. And so let's say we've got a positive charge here, and let's just say it's a 1 coulomb positive charge to make the math easy. So my question is if it was at this location right up here where the electric potential is 50 volts, then what would be its potential energy? Well, again, it's just Q times V for potential energy, and Q is 1 coulomb times 50 volts would get you, in this case, 1 joule. So keep in mind a volt is a joule per coulomb times coulombs will get you joules. And so it'd be 50 joules. So, and at this location at 40 volts, the potential energy would be 40 joules, 30 joules, 20 joules, 10 joules, 0 joules. And so this positive charge, if I'm holding it in place right here, so given where what the potential is on this kind of scale here, where would this lovely positive charge go if I let it go and it naturally goes where it wants to go? Well, it's going to want to go down because its potential energy is going to go down in that direction. So if I want it to go up, I'm going to have to apply a force in that direction. Same thing with this marker. If I drop this marker, it's going to go down. If I want it to go up, I'm going to have to apply a force in the upward direction and cause it to go up, if you will. Spontaneously, it wants to go down because it lowers its potential energy. Same thing is true for this positive charge right here. Now, on the other hand, unfortunately, let's say we take a look at a negative charge. So, and here's where things go a little awry because we don't have any such thing as like positive mass and negative mass. So there's nothing analogous in gravity here. But with a negative charge, and let's say once again that this is also -1 coulomb to make the math easy. And so we can see here that what would its potential energy be at, say, the 30 volt point? Well, -1 coulomb times 30 volts is -30 joules. And you can have negative potential energy. So in fact, negative charges always have negative potential energy if they're in a positive electric potential, an area where there's positive electric potential. But if they're in an area where there's negative electric potential, they can actually have positive potential energy and so on and so forth. So things get a little bit hairy. So with gravity, we only ever experience positive potential energy, not the case with electrical potential energy. All right, so here we can see that it'd be -50 joules, -40 joules, -30 joules, -20 joules, -10 joules, and 0 here. And keep in mind, I had to scale down to 0. There could be another point down here where let's say it's like -10 volts. Again, potential is not bounded to being just positive numbers. So the question is, how does this negative charge now lower its potential energy? Well, in this case, in going from -30 to -20 to -10 to 0 and then to +10, that would actually be raising its potential energy, not lowering it. And we're going to find out that for the negative charge, it actually wants to move in the opposite direction in order to lower its potential energy. And so in this case, it's going to go from -30 to -40 to -50. It's getting more and more negative. Getting more and more negative means you're going lower on a potential energy scale. So it seems a little bit tricky, a little bit backwards, but that's the way it works. Now, if we kind of look at how you get a scale like this in voltage or electric potential, again, I should say, how would that be even possible? Well, it'd be possible, let's say, if you had positive charge up here or a negative charge down here. And the closer you are to the positive charge, the more positive the potential. The closer you'd be to the negative charge, the more negative the potential. Either one of these could be true or both, depending on the case. And if you look at it in that context, and you look at this back in the context of Coulomb's law, you'd be like, well, yeah, Chad, the positive is going to be repelled from the positive and attracted to the negative. And it's easy to see in that context. And the negative is going to be repelled by the negative and attracted to the positive. And so, yeah, it would want to spontaneously go that direction. And that's easy to see. But now you need to recognize it in terms of electric potential as well. So for a positive charge, to get lower potential energy, it moves to lower potential. It was defined for a positive charge. But for a negative charge, to get lower potential energy, it goes to higher potential. And so it makes sense for the positive charge. It's exactly backwards for the negative. And again, we don't have an analogous situation with gravity because there's only mass. There's not positive mass and negative mass. If there were such a thing as negative mass, if I let it go, it would go up, not down. But we don't have that situation. So only the analogy with gravity only goes so far here. But you do need to understand this. Again, for a positive charge, it spontaneously goes to lower potential to lower its potential energy. For a negative charge, it will spontaneously go to areas of higher potential to lower its potential energy. So keep that straight. All right, so a couple other things we want to take a look at here. So for an electric field, the force exerted on a charge in an electric field is equal to QE. So, and we want to talk about work for just a second. So in an electric field as well, and work is equal to force times displacement, if you recall. And in this case, I want to look at displacement. I'm going to actually use a D for it. It's commonly used in this chapter in many a textbook, even if it's used as delta X in other places, but I'm going to go with the same convention here. So work is force times displacement, and here force is Q times E if it's work being done by an electric field. So I can go from there, and there's our work. Now, what I want to take into account here too is that we've got another expression for work when it's done in a by a conservative force in this case. And a conservative force, you might recall, gravity was just such a case. And if it's the only force acting on something, then mechanical energy is going to be conserved. Now, if you recall the work energy theorem for just a second, work energy theorem says that work is equal to the change in kinetic energy. So keep that in mind. That's not new. We've seen that before. And you might remember that we actually saw that in a conservative, when you're dealing with a conservative force, work is actually equal to the negative of the change in potential energy. We can kind of see why that is in just a sec. So if the only force acting on an object is a conservative force, then mechanical energy is conserved. And one way to express that is that to say that the initial total mechanical energy, the kinetic and potential combined, equals the final total mechanical energy, the kinetic and potential final combined. Another way to look at that, though, is if you rearrange it a little bit, you can see that there's a relationship between the change in kinetic energy and the change in potential energy. And they are equal in magnitude, but opposite in direction. If we take a look at it, and again, in the context of gravity, if I let go of this marker, it's going to fall. And as it falls, its potential energy goes down, but it speeds up and its kinetic energy goes up. And in fact, the kinetic energy it gains is exactly equal in magnitude to the potential energy it loses. And so these changes aren't equal. They're equal in magnitude, but they're in the opposite direction. So they're opposite signs. And so you can say that the change in kinetic energy is equal to the negative of the change in potential energy. And that's where this kind of expression comes from. So we have the work kinetic energy theorem. And as long as we're dealing with a conservative force, that change in kinetic energy is going to be equal to the negative of the change in potential energy as well. And so in this case, we got an expression for that, right? So the change in potential energy was Q times the change in electric potential, carry the negative sign, and so it's negative Q delta V. And now we have a formula for work done by an electric field as well. So in this case, that could be positive or negative work, depending on the sign for Q and depending on the sign for delta V. If you're going to an area of higher potential, delta V is positive. If you're going to an area of lower potential, then delta V will end up being negative. And it's always just final minus initial, but you got to kind of keep that straight. All right, I think we're ready to do a little bit of plug it and chug. Actually, we got one other thing to derive, my bad. We've also got this expression for work over here, QED, and a new expression for work here, negative Q delta V, and they're equal. So negative Q delta V. If we set those equal, we can see that the Q is going to fall out, and we can derive a new expression for delta V here as well. And as long as we're in an area where there's a constant electric field, so delta V is going to equal negative ED. So in such an area where you'd have a constant electric field, we'll find out is in a parallel plate capacitor, and we'll visit those in the next lesson. So in such a case, you get a simple relationship so that the potential difference is proportional to the electric field and proportional to the displacement. A point charge is moved as well. So three variables, you might be provided with two and do some plugging and chugging to get the third is kind of where that comes up. All right, but we'll probably visit that more in the next lesson than in this one. Let's get back to doing some plugging and chugging here. So the next question says, an electron, and then the charge and the mass are provided in parentheses. Q equals negative 1.6 times 10 to the minus 19 coulombs. M equals 9.11 times 10 to the negative 31 kilograms. Is accelerated from rest through a potential difference of 1.0 times 10 to the negative 6 volts. What is its final velocity? And so we want this final velocity, which is a part of the kinetic energy formula, if you recall. And we're given enough information, given the charge and the potential difference to which it's accelerated, to get the potential energy change as well. And we know how to relate potential energy change and kinetic energy change. And so in this case, we've got the change in kinetic energy and the change in potential energy. And again, they're not necessarily equal, but one goes up, the other goes down. They're equal in magnitude, opposite in direction. And we derive this a couple different ways. We could use the work energy theorem, and as well as the work in an electric field here to say that delta KE is equal to the negative of the change of potential energy, which will then take a step further and say is negative Q delta V. So, and then your change in kinetic energy is going to equal 1/2 mv final squared. And then the initial, since it started from rest, the initial 1/2 mv squared is going to be 0. Initial velocity was 0. And we can do some plugging and chugging here and plug some numbers in. So we'll get 1/2. The mass of the electron was given as 9.11 times 10 to the negative 31 kilograms. If it wasn't already in kilograms, we'd have to get it there. Times that final velocity squared equals negative. And then Q, and plug that in, you got to be careful. The charge itself is negative. That negative sign is part of the equation. But when you plug in Q, in this case for an electron, it's negative 1.6 times 10 to the negative 19 coulombs. and then times delta V. And in this case, we weren't told V final or V initial. If we were, we could actually, do V final minus V initial. But we're told it was accelerated through a 1.0 times 10 to the minus 6 volt difference. So 1.0 times 10 to the negative 6 volt. It was given as a positive change. That means the overall electric potential went higher, and that's why it's being plugged in as a positive value for delta V. If it was said it was accelerated through a potential difference of negative 1.0 times 10 to the minus 6 volts, well, again, a negative change would be a great way to accelerate a positive charge. It would not be a great way to accelerate a negative charge. For a negative charge, I do need the potential to go up, a positive potential difference, in order to lower the potential energy and have it go faster and faster and faster and accelerate. So the numbers here do make sense. So don't forget to multiply that negative times a negative, but we'll let our calculator do the heavy lifting from here. And so negative times a negative is a positive, so I'm going to have 1.6 times 10 to the negative 19 times 1 times 10 to the negative 6 times 2, or divided by 1/2, however you want to look at that, and then divided by 9.11 times 10 to the negative 31. Make sure I got all these numbers correctly. 6 times 2 looks good to me. And then I'm going to take the square root of that number and get 592.67, which in this case we want to round to 2 sig figs, it looks like. So 590 meters per second. So the next two questions are going to involve this lovely diagram right here, provided as part of the question. The first question says, what is the electric potential at the empty corner of the square in the following diagram? All right, so once again, it is very nice that electric potential is a scalar, not a vector. So we're going to have 3 different contributions from 3 different point charges. We learned how to calculate the electric potential contributed by a point charge very simply. If the Q value is positive, the potential comes out positive. If the Q value is negative, the electric potential comes out negative. And we're just going to add up their magnitudes. There's no vector math here at all. No breaking up into components, no Pythagorean theorem, at least not as far as adding vectors or anything like that. We're just going to add the scalar magnitudes together. We'll get a positive contribution from this positive charge. We'll get 2 negative contributions from these 2 negative charges. And again, the location where we're trying to do this here is at this empty corner right there. And so we've got 3 different point charges that can contribute, and we're simply just going to have KE Q1 over R1 plus KE Q2 over R2 plus KE Q3 over R3. And we'll just simply add the 3 contributions, those 3 scalar quantities together. All right, so I'm going to keep writing KE as KE instead of writing 8.99 times 10 to the 9th. But that's what I'll be plugging into my calculator, but we'll keep it a little simpler on the board, keep it looking fairly clean. And I'm going to start with Q1 and then Q2 and then Q3. It's arbitrary, it doesn't matter what order you add these in. But Q1 therefore is the positive 4.0 nanocoulombs, so 4.0 times 10 to the minus 9 coulombs. And R1 is going to be that 1 millimeter distance, so to that empty corner. And so 1 millimeter would be 1.0 times 10 to the negative 3 meters plus KE. And here's the hard one, right? Because we don't actually have the distance, but the distance is the diagonal along that square. So we could just look at it, the hypotenuse of a right triangle, and say, well, 1 millimeter squared plus 1 millimeter squared equals the hypotenuse squared, and find out that it's equal to the square root of 2 millimeters, or 1.414 millimeters, so to speak. All right, we'll plug those in. And so the magnitude of the charge was the negative 2.0 times 10 to the negative 9 coulombs. Again, the negative sign, you got to get that sign in there so that the whole term comes out negative. And then that's going to be 1.414 times 10 to the negative 3 meters. That's the square root of 2, which I did in my head, or I had memorized anyways. But if you don't have it memorized, you'll definitely want to plug that into your calculator as well. So, and I'm carrying extra sig figs here, but obviously at the very end of this problem, we're just going to limit ourselves to 2 sig figs. All right, then finally for Q3 here, so KE times negative 1.0 times 10 to the negative 9 coulombs, all over again a distance here of 1 millimeter, so 1.0 times 10 to the negative 3 meters. And we'll just add these terms together here. So in fact, I'm going to add them separately, calculate them separately, and then add them together as well. So 8.99 times 10 to the 9th times 4 times 10 to the negative 9 divided by 1 times 10 to the negative 3. We're going to get 35,960. That's joules per coulomb or volts. Next one here, I'm going to use the entry function, so 8.99 times 10 to the ninth times -2 times 10 to the minus 9, and divided by 1.414 times 10 to the -3. That's going to get me negative 12,716 volts, or again, joules per coulomb. And then finally our last term here, and I'm going to use that entry function yet again. 8.99 times 10 to the ninth times -1 times 10 to the -9 divided by 1 times 10 to the -3. And we're going to get negative 8990 volts. And we'll add all these together. So again, 35,960 minus 12,716 minus 8990. We're going to get 14,254, which if we round to 2 sig figs should get us to 14,000 volts. Cool, let's take a look at that second question. Second question says, what is the potential energy of the following arrangement of point charges? This is a fairly common problem in this section and one of the more challenging ones to solve. It's not super bad, it's just a little bit tedious and long. But if we're trying to find the potential energy of this arrangement of point charges, what we're going to envision then is bringing each of these to their location one at a time. So, and when you bring the first one in, there's nothing else around, and so it doesn't cost you any energy to get it there. So, but let's say we brought this negative point charge in first. So it doesn't cost anything. There's no other point charges attracting it or repelling it. But then we bring in this negative charge. And if we bring in this negative charge from infinitely far away to this location, well, it's being repelled by this one. And that's going to cost energy. There's going to be work done to get it there. And we can figure out what that work would be. So, and then we're going to bring the positive charge in. Now, this positive charge, on the other hand, though, is actually attracted to both these. And so rather than costing work, so it's actually going to release energy as it comes. It'll end up being negative work is the calculation. So, and we'll then add up the contribution. So again, the first one's free, but there's going to be work done, either positive or negative work, depending on the situation, to bring in the other two. And we'll calculate that in and add it together for those two steps. Let's see how this plays out. All right, so the potential energy of a point charge is equal to the magnitude of the charge of that point charge times the potential it's in. But the potential that it's in is due to the presence of another point charge, the magnitude of which that potential is KEQ over R. And so if you have Q of the point charge in question times that KEQ over R of the other charge that's affecting it and causing it to experience a potential at its location, you end up with potential energy equals, in this case, KQ1 Q2 over R. And again, be careful. This looks very familiar to Coulomb's law, but again, it's over R, not over R squared. All right, so bringing in the first point charge here doesn't cost anything. So again, if these two charges weren't here, and I just brought this first one in from infinitely far away to that location, there's nothing attracting it or repelling it, there's no other point charges, and there's no energy change associated with that. So when it's infinitely far away, the potential is 0, and when I get it to that location and there's no other charges around, its potential is still 0. So, and if the potential is still 0 the whole time, so then the change in potential energy is also 0. So no change in electric potential, no change in potential energy therefore as well. All right, so now we're going to bring the second point charge in. So when I bring the second point charge in, the only other point charge around is this one. Now again, it comes from infinitely far away, and when it's infinitely far away, so you can say that the R is infinity here, well that means the potential energy is 0. So it makes a great reference point here, and then we bring it all the way to this exact location, and so we're getting this change in potential energy from when it's 0 to when it reaches its final value. And it's just going to, again, have a value of KQQ over R. And so in this case, we got our K, and then we've got the negative 2.0 times 10 to the negative 9 coulombs times negative 1.0 times 10 to the negative 9 coulombs, all over that 1 millimeter, 1.0 times 10 to the negative 3 meters. And again, we could probably do the math here on our own here. So 2 times 1, or negative 2 times negative 1 is 2. 10 to the minus 9 times 10 minus 9 is 10 to the negative 18. Divided by 10 to the negative 3 is going to be, you know what though? We got k over there. I'm just going to let my calculator do heavy lifting. I retract. I'm not doing this in my head. So 8.99 times 10 to the ninth times negative 2 times 10 to the negative 9 times negative 1 times 10 to the negative 9 divided by 1 times 10 to the negative 3. Yeah, it looks good. 1.798 times 10 to the minus 5. And that's in joules for change in potential energy. So that's the potential energy of the system now, the pair of charges as it exists. And now we'll bring in charge number 3. And once again, we've got Ke. So, and now I've got to factor in bringing in charge 3 to this position, again, from infinitely far away where there was 0 potential energy, to this location here, where it's going to have a potential energy contribution from its proximity to charge number 2 and from charge number 1. So let's look at it relative to charge number 2 first. And so in this case, it's going to be 4.0 times 10 to the negative 9 coulombs times negative 2.0 times 10 to the negative 9 coulombs, all over a distance separation of 1.0 times 10 to the negative 3 meters. And then we'll add this to Ke times 4.0 times 10 to the negative 9 coulombs times negative 1.0 times 10 to the negative 9 coulombs, all over, and again, that's the diagonal, the distance between them, which we figured out earlier was the square root of 2 millimeters, or 1.414 times 10 to the negative 3 meters. And if we take a look at this first term is going to come out negative since one of the two charges is negative, and so is the second term since one of the two charges is negative as well. And so the contributions here are going to be negative potential energies. And again, that should make sense because we're dealing with attraction here rather than repulsion. And so rather than costing work, there's a release of energy instead. All right, so we got 8.99 times 10 to the ninth times negative 2 times 10 to the negative 9. Let's get the first one in there, my bad. Times positive 4 times 10 to the negative 9 times negative 2 times 10 to the negative 9 divided by 1 times 10 to the negative 3. We're going to get 7.192 times 10 to the minus 5. Negative, that is. Joules. And again, 8.99 times 10 to the ninth times 4 times 10 to the minus 9 times negative 1 times 10 to the negative 9, and then divided by 1.414 times 10 to the negative 3. And now we're going to get 2.543 times 10 to the minus 5. And again, that's also negative. And we can add up these two together. We're going to get 9.735, or negative 9.735. Times 10 to the negative 5 joules. So we got a negative contribution for bringing charge number 3 in, positive contribution for bringing charge number 2 in. We'll add them together and we can see that the negative contribution here is going to be larger than the positive. We're going to get negative, if we round to 2 sig figs, negative 7.9. Times 10 to the negative 5 joules. Cool, and that is the total potential energy of that arrangement of atoms. And this should make a little bit of sense. We probably could have predicted that it was going to come out negative because if you kind of said, is this going to be dominated more by repulsions or more by attractions? And because the positive charge is being attracted to two negatives, and it has the largest magnitude, looks like there's going to be much more attraction here and here than the repulsion that's going to be experienced here. And so we should have predicted in all likelihood that it would end up with an overall negative potential energy. It means this would not cost any energy to form. In fact, it would release energy upon forming. If you found this lesson helpful, consider giving it a like. Happy studying.